Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to go over my second practice problem using an ice table. And in this problem we're going to be able to use what is called the X is small approximation. And then we'll need to use the 5% rule to calculate whether that approximation is valid. Okay, so here's my second problem. Says in the following reaction, your Keq or your K is equal to 9.3 times 10 to the negative 7 at room temperature. And you calculate the equilibrium concentration. It's asking you to calculate the equilibrium concentration of N2O4 in a flask that initially has only 3.00 moles of NO2. So they give you the balanced equation here. It's an equilibrium, or it's not an equilibrium. We'll find out what the equilibrium concentrations are. But here's our balanced equation, and they tell us what the Keq. Now, notice here that the Keq that they're giving us is very, very small. In my previous video where I did the practice problem number 1, Keq is very large, and so you couldn't use this approximation because your X, your change, was going to be very large because when we have a large K, that means that the products are going to be much more favored over the reactants, and so a lot of your reactant is going to change to go to product, and so the X is small approximation wouldn't work in that case. But here we have a pretty small Keq, so it's a good chance we can use the X is small approximation. So let's get into this problem. So the first thing I'm going to do is I'm going to set up my ice table like I did before. So here I'm going to write I, C, E. And then I'm going to fill in the initial concentrations that I was given. So it says that I start with only 3.00 moles or molar of NO2. So I start off with 3.00 molar here. You don't have to write the molar because it's assumed that you're going to have concentration in molarity. Again, you want to use concentrations. You don't want to use moles for your ice table. Okay, and then we're said we only have the NO2, so that means that the concentration here is 0 to start with. So since we have 0 product, that means that the initial reaction has to go this way. So that means our change in X, our X is going to be here negative, so we're going to subtract a certain amount here because some of our reactant is going to become product. So we're going to lose some here. So we're going to call that X. So how much did we lose? We lost an X amount. So we're going to subtract X from here. Now, one thing I want to point out right now is, I mentioned this in my last video, but here, notice that I have 2 moles of NO2 produces 1 mole of N2O4. Because of the coefficients here, we need to use the same stoichiometric amounts as we find in the balanced equation. So this isn't going to be minus X, it's going to be minus 2X. So I have a 2 coefficient here, so I should have a 2 coefficient here. So I'm going to lose 2X amount here, but I'm going to gain a 1X amount here. So this is going to be plus X. So for every 2 moles of NO2 that I lose, I gain 1 mole of N2O4. So if I lose a 2X amount here, I'm going to gain a 1X amount there. So then I write the expressions for my equilibrium. So this one's going to be 3.00 minus 2X. And this is going to be 0 plus X is X. So I've got my equilibrium expressions for the concentration of NO2 and N2O4. So now I'm going to write out the K expression. So the K expression for this is going to be K EQ is equal to, and then it's going to be the concentration of N2O4. So concentration of N2O4, again, raised to its coefficient, which is 1. So that's a 1. We don't write that. And then over the concentration of the reactant, and that's going to be NO2. The concentration of NO2 raised to the power of its coefficient, which is a 2. Sorry about that. So we're going to put a power of 2 there. So there's my K expression. So now I'm going to take my equilibrium expressions in terms of X and plug them in here. And let's remember that the Keq here is equal to 9.3 times 10 to the negative 7. So we have 9.3 times 10 to the negative 7. So then this is going to be equal to, well, N2O4, the concentration, that's going to be X. So that's going to be X over, and then here we have NO2 squared. So we're going to put in 3.00 minus 2x squared. And so now we have 9.3 times 10 to the negative 7 equal to this expression here. So we could then, at this point, use the quadratic formula because we're going to get a quadratic equation here. But one thing you should notice is that if we look at the Keq, it's really small. That means that the reactants are going to be much more highly favored in this reaction. That means that very little of this is going to form N2O4. So X is going to be really small. Is it small enough to ignore? Possibly. How can you tell by looking at the problems here? The best way, or maybe the easiest way to see if it's going to work, is to compare your Keq with your initial concentration. If the initial concentration and your Keq differ by 1,000 or more, then it's a good chance that your ignoring of X being small, X is so small that it's going to be negligible that you could ignore it here, then that's going to be probably going to be valid. You're still going to want to check it, but we can make that assumption. So if the factor of your initial concentration and your K is maybe 100, then maybe it's valid, but you'll have to check it. So let's go ahead. This is well, the factor here is well more than 1,000. I'm going from 3 to 10 to the negative 7, right? So that's a very large difference. So this means that X is going to be really small, and so that means we can ignore it, but we'll have to check it with the 5% rule. Okay, so let's go ahead and eliminate the X, this part here. So we can get rid of the 2X, and then that's going to simplify to X over 3.0. So, I forgot the squared there. So you don't forget the squared, so it's going to be 3.00 squared. So notice how that has become a much easier problem to solve than having to use the quadratic formula. So now all I need to do is multiply both sides by 3 squared, which is 9, and then I'll get my X. So in this case, X is going to be equal to, what did I get? 8.37 times 10 to the negative 6 molar. So that's my X value. Now, is this a valid assumption? Well, how do I check it? I use the 5% rule. What's the 5% rule, you ask? Well, I'm glad you asked. So the 5% rule is that if you take, we'll do a 5%. You have to do a 5% rule check or 5% check. So what is the 5% check or rule? The 5% rule is basically a way of verifying that your assumption here is valid. And what is that? So you take the x that you got. So whatever your x value is, you're going to divide it by your initial concentration. So whatever the initial concentration you are given for your reactant, right? And then you're going to multiply that by 100, and that answer, you're going to get a percentage. So that percentage should be less than 5%. If it's less than 5%, then it's valid. If your percentage is 5% or more, then it's not going to be valid. So if we check this, we take our x, which is 8.37 times 10 to the negative 6. We're going to divide that by our original concentration, which is 3. We have that molar, that molar. And then we're going to multiply by 100. And the percentage we get, is going to be 2.79 times 10 to the negative 4%. So that is well below the 5%. So that indicates that my assumption here that x is small, that it's so small it's negligible, we can ignore it, is valid. So now I have my x. So I verified that that is correct. So now I can go ahead and plug it into my numbers here. So this x is here. So it's asking, what is the equilibrium concentration of N2O4? Well, the concentration of N2O4 is x, which is this. So this is the concentration of N2O4. If I wanted to find the concentration of the leftover NO2, I would take the 3.00 and then subtract 2 minus, subtract 2x. So I'd multiply x by 2, then subtract that from 3.00, and then that would give me my concentration of NO2 at equilibrium. Okay, so that is how you do a problem with the x is small approximation. So, and then always double check with the 5% rule. So even if you're sure that it's going to be valid, always double check. And then you could always, even if you think it's not valid or may not be valid, you can go ahead and do it anyway, and then just do the 5% rule just in case. Maybe you're right. But you always want to do the 5% rule to double check if it's valid, because if it's not valid, that means that you got to go back and redo it with the x in there, which means you're going to have to do a quadratic formula, or you could do the successive approximations. So that's it for this video. I hope this was helpful. If you enjoyed this video, then please, by all means, like that video, hit that like button right there. Also, make sure you subscribe to my channel, hit that notification bell, and make sure you click all when you do, so that way you can be notified by all the videos I put out. And then finally, what you want to do is put a comment down below and ask me any questions you have, make any comments that you have about my videos. Anything is appreciated. I look forward to hearing from you. Thanks and have a great day.